All right, welcome. In this video, I want to talk a little bit about emergence in elementary cellular automata. So to get us started on that, I'm going to have to just introduce a little bit what is an elementary cellular automata, and then we can start talking about emergence in one. So imagine that we have an infinite line of cells like this one depicted here, infinite in both directions. And imagine that each of these cells then could either be alive or dead. And in this depiction, I'm using black cells to indicate living ones and white cells to indicate dead ones. Now, a cellular automata will evolve, so this might be its current state, and there will be rules that are used to determine its next state. And the next state will determine which cells, for instance, might be born, or which ones might die, or which ones might stay alive. So, for instance, the next state of this particular state might be this one here, and I've just used a very simple example here where all of the living cells move to the left. So just one more time, we'll just see all of the living cells just move to the left, and that's just one example of a cellular automata. There might be one rule that simulates these living entities moving to the left. There might be another one that simulates them moving to the right, and there's a bunch of rules that might simulate other kinds of patterns as well. So this type of system that I've just described is a cellular automata, or an example of a cellular automata. And because it's a very simple one, it's one-dimensional and so on, this is an example of what we sometimes call an elementary cellular automata, which is a very simple kind of cellular automata. And these cellular automata, the elementary kind, were first studied in detail. I don't think they were necessarily first introduced, but definitely this version or variant of a cellular automata was first studied in detail and introduced by Stephen Wolfram in his 2002 book, A New Kind of Science, which you see here. He also studied them earlier. He published some papers on them, I believe in 1983, or definitely in the 1980s. But he put all of his work together into this interesting tome, which today is still considered to be a very important piece of science, and a new kind of science. He said he was hoping it would change science. Well, it's got an important place in complex system science and some of the related fields. You might also know Stephen Wolfram maybe more from his commercial side. In the 80s and 90s, he developed a mathematical software called Mathematica. And if you happen to have done any sort of mathematical work or study in the last 20 years, it's possible that you have used his website, Wolfram Alpha, to help you with your mathematical work. I use it, for instance, often to compute sums that I don't want to compute by hand, but others use it, for instance, to help them with their calculus homework or whatever else you might need in the mathematical space. Wolfram Alpha is a very powerful tool to do it. So not only is Stephen Wolfram a scientist who studied these elementary cellular automata, but he's also made important contributions to software development in mathematics. So the elementary part of the elementary cellular automata is sort of defined by the simple nature of these automata that we're talking about here. As I've already mentioned, two important simple features are one, that it's one-dimensional, so the cells are arranged only in this one long line of cells. We don't, for instance, have a grid of cells or a three-dimensional volume of cells. And then also, we limit the states of the cells. So an automata is something that can change from state to state. Well, we've limited it to only two states. Well, we could imagine automata with more than two states, and there are more sophisticated cellular automata that have more than two states. The final important piece for the elementary cellular automata is a restriction on the kinds of rules that we could apply for their evolution. Now, in general, there are infinite possible rules we could have even for a simple one-dimensional two-state cellular automata. So Stephen Wolfram decided in his own investigation he wanted to sort of explore a bunch of these rules, but since there are infinite of them, that's sort of a wide space to explore, he decided to limit his exploration down to a subset of these rules. And so he decided to restrict his rules by using what is sometimes called the principle of locality. And this is something that we believe to be true in our own universe, which is the idea that an event can only be affected by things that are close by in its locality. And so for that, to apply that in our cellular automata, we will say that the state of a particular cell can really only be impacted or determined by the states of other cells in its local area. Its local area in this case, we're going to define to be the cell itself and its immediate neighbors. So it's two immediate neighbors, its left neighbor and its right neighbor. So we can sort of see here in this depiction here that I've got one such rule depicted as Stephen Wolfram usually depicts it as the next state you would get in the last state. So imagine this was the last state here. This depicts a state where in the last state the cell was alive, but the two immediate neighbors were also alive. And this rule is saying that if this were the state in the last state, this is the locality in the last state, then in the next state the cell will be dead. It doesn't say anything about what happens in the left and the right here. That's because what happens in the left and the right cell here depends on their locality, not this locality. So we would need to check that another cell to the left or another cell to the right to determine. So this only determines the next state of the middle one, but in determining the next state of the middle one, we need to know the state of its two immediate neighbors as well. And you can see here that there are 8 possible patterns that we could have come up with our grid patterns here, where we've got all dead up to all possible combinations up to all alive. And for each of them, we've stated what the next state would be. So there's 8 possible ones, and for each one, we've stated whether the next state would be dead or alive. Now, as you can imagine here, by changing what the next state is, I could get a different rule. If I change this, instead of being dead, I change it to being alive, I've got a different rule now. And a different rule is going to evolve in a different way. The next state would be different if I change my rule. So as noted, there are 8 configuration cases. There are 8 possible last cases or initial cases. And then for each of them, we need to state what the next state is. So there are 8 cases that we need to state. Now the next state, since it's just going to be alive or dead, and there's only 2 possible states that it can result in, that means that there are going to be 2 to the power of 8, because we have 8 cases, 2 to the power of 8 possible rules. And so that's 256 possible rules. And so what Stephen Wolfram did in his investigation was he decided, well, why don't I go check out each one of these different elementary cellular automata, there are 256 of them, and check them out and see what they do, and see if they're interesting. And on the face value, there is no immediate reason why we should suspect any of them are interesting at all. They're very simple. And often things that are very simple are not very interesting because they're very simple. Now, in order to sort of formalize this, and he actually then wrote a few simple programs to simulate these automata, he decided to actually start encoding them in a specific way. As you can see here, if we kind of read this off, if we read them off as dead being zeros and alive being ones, then this can be read off as a binary number, 0, 0, 0, 1, 1, 1, 1, 0, or written here in binary, which when translated into decimal is the number 30. And so this rule here, he would call this one rule 30, and then he would, look at it for a while and see what it does, and then maybe go to the next rule, which would be rule 31, which we get by flipping this bit, and he would try that one, and he did it for all of the 256 rules from rule 0 up to rule 255, and he basically just saved the output into a data file and went and visually looked at them to see what's going on here. Is there anything interesting? And of course I wouldn't be telling you about this if there wasn't something interesting, so indeed he did find something interesting. And it is on this rule. This rule is rule 30, as I mentioned, is a very important rule because it has some chaotic patterns of behavior that emerge from it. Some of the other rules do too, but this one is particularly important. And I'll talk a little bit about that more when we investigate this rule in more detail. All right, so like Stephen Wolfram, I've gone ahead and I've written a little simulator of his cellular automata, the 255 elementary cellular automata. And I can just enter in a rule here if I want to, and I can fire off the reset button, and well, let's just see. it will simulate the automata for me for about 100 steps until it fills up this graphic here, and then I'm done. And as you can see here, at least the initial state that I've got here, we can see the first one up at the top. I just started off as Stephen Wolfram did. I actually made this a 201 wide, so I have one center square, and I made the center square alive. And what we saw here is that after one step, the center square died, and all the other squares were dead already, and then it just stayed dead for all over 100 simulations. So this is one of the example rules that Stephen Wolfram had that he would maybe categorize as sort of a boring rule, or at least he might have said it's boring. I say it's boring in the sense that the performance is not very interesting. It's not something to be excited about, and in fact it's very predictable because this is rule 0. Rule 0 has a 0 in every one of those locations, and basically what that means is no matter what the original state was, the next state is dead. No matter how you got here, you would be dead. So I'll give you another example of showing that, is that even though Stephen Wolfram, you could start this on any possible input, right, of living and dead cells, but to restrict his exploration a little bit more, he decided to only investigate this one sort of starting location with one living cell. But I've decided to also add a little button that says, what happens if I start it with random cells? Meaning just filling in those initial 201 with just alive or dead flipped at random. And as we can see here, that for rule 0, yeah, indeed, they all just died because that's what we should expect. No matter what the initial pattern was, we end up with a dead pattern. So that is, again, maybe not very interesting. On the other side of the spectrum, we sort of have the opposite, and this is pointing out something interesting as well, that in this space, in the elementary cellular automata space, we sort of have a symmetry that because it was arbitrary that we said sort of black was alive and white was dead, or vice versa. 0 and 1 is usually how we represent this in the code. We could just flip those so that, you know, whatever, 0 is alive and 1 is dead, and we would just get the exact same behavior with a symmetric rule. And that's what I have here. This is rule 255. That's where we put 1s in all of the spots instead of 0s in all the spots. And perhaps not surprisingly, that means no matter what our last state was, the next state will be born, will be alive. And so, as we can see here, both with the initial starting and with the random starting, everything just ends up alive. And so, just like rule 0, maybe not very interesting. So now we can try rule 1. Rule 1 is a little bit interesting, but maybe not going to say too much about it. Whereas the last two were fixed point attractors, everything was dead or everything was alive. That's, again, borrowing our dynamical systems language. These are attractor states, and so everything alive or everything dead are fixed point attractors. This one is sort of an oscillator. It oscillates between two different states over and over again, and that's maybe more like a limit cycle in that dynamical systems language. And so that's interesting, I guess, maybe a little bit more interesting than the last one state, but still not super interesting. So like Stephen Wolfram, we're sort of going through his process. He did this, he went through rule 0, okay, not cool. You know, file that. Rule 1, what's going on there? Rule 2, now this one I do find a little bit more interesting because at least on the initial state, we see that what it does is it takes that original living cell and moves it to the left. And so we might think to ourselves, hey, this might be like that example rule that we had in the slides, the moving to the left example rule. So let's try it. Unfortunately it's not, but let's do a quick test. I'll just try it on the random one and see what happens. It doesn't quite move everything to the left, but it moves sort of like the left-hand edge-ish of most of them. Yeah, you know, it does something. It's not quite moving everything to the left. And so, again, maybe not super interesting, but maybe a little bit more interesting than the last couple that we looked at. Maybe another thing I'll comment about all of these rules that we've looked at so far is that after running them for a couple of steps, we can probably predict what the next one's going to look like without even knowing what the rule is. For instance, now that I see this pattern, another test we could put is I've done 100 here. Could you predict what the state would look like after, say, 10,000 steps? And if you think you could do that without running it forward, then that means we have a pretty predictable closed system here, a non-chaotic system. And so far, that's what we've seen. Now, again, I mentioned here, maybe we think this one is moving to the left. This one's not moving to the left, but I thought to myself, hey, one of these rules is the moving to the left rule. There is one of these rules that will just move everything to the left. So I went and I sat down, and instead of trying them all out like Wolfram did, I just analytically decided, well, what would that rule look like that would move everything to the left? And I found out that that rule would be rule 170. So let's try that. Again, on our initial state, well, that's exactly the same thing that rule 2 did. So let's try it on the random state. And yes, it looks like it's moving everything to the left here, okay? Now again, remember in our stipulation, this is supposed to be an infinitely wide screen here, an infinitely wide cellular automata, but of course for practical reasons in my simulation, I've only made it a finitely wide such automata, and that means it's treating its most rightmost cell and the leftmost cell. There's always a dead cell to the left of it, and that sometimes throws things off, or at least here it doesn't really throw anything off, but that's why we see all these dead cells creeping in here. We probably can predict where we're going to be on this example in 10,000. We're all going to be dead because of, everything is moved to the left. But if we actually had an infinite long one, we would need to know what was that cell 10,000 to the right of us. If that one was alive in the initial state, then it will be alive in that step 10,000. So even though we might not be able to see it immediately from here, we should be able to predict the state 10,000, the 10,000th state, without having to go through the intermediate states. And so this is still, again, a predictable pattern, even though it's interesting. All right, I'm going to skip rule 3 just because it's not very interesting either, but I thought rule 4 was interesting. Rule 4 looks like it just copies the state down from the one above. And again, just because it looks like that for this particular initial state doesn't mean that's what it does. So let's try it on the random, and we can see that, yeah, no, it doesn't really do that. It looks like it copies down only the single ones, the single living states that had no living neighbors. And okay, that's interesting maybe in some regard, but maybe again, we do want to know that identity rule, the rule that just copies it down. So I went again and I just sort of analytically decided what it should be, and it should be the rule 204. So I calculated that, and again, here we are with the initial state. Well, that's not surprising, that's what rule 4 did, but running with the random initial state, okay, so it copies it down. Again, maybe interesting in the sense that, okay, at least we know that's what this rule does, and it's identifiable as what it does, but again, is it like cool? Is it, is it something that is exciting, that is worth writing a 1,000-page book about? Probably not. So we probably skipped over this rule as well. I'll just continue this theme a little bit. If we skip to rule 16, and you'll probably have a guess why it is rule 16 and not rule, say, 5 or 12. We got this one moving to the right, which again, we might, you've probably seen this one before, but it's not actually going to move us to the right because it only worked for that one initial state. So again, just to finish the trilogy, the moving to the right rule is actually rule 240. And again, just testing it on the random one, we can see indeed it does move everything to the right. So if these are not really the interesting ones, then where do the interesting ones lie? Well, maybe like, Stephen Wolfram, we could try and iterate through all 256 of them. That seems like it's going to take a lot of time. He already did it for us and he wrote a big book about it. So I guess we can probably just look up in that book and see which ones are cool. The next one that I thought was cool is rule number 22. So let's take a look at that one. So this is a real cool pattern. This is a pattern that's well known, and it has a name. It's called the Serpensky Triangle, and it is a fractal pattern. It's a fractal pattern. You can form it two ways. Apparently, one way you can do it is with Rule 22 of Stephen Wolfram's Cellular Automata. But another way to do it is to start with a triangle. Any triangle is fine. An equilateral triangle is usually the one we'll use. And then what you do is you draw a another triangle upside down inside of it. And when you do that, you end up with 3 triangles, the Triforce from Zelda. And then you can go ahead and take each one of those and make a new 3 triangle Triforce and so on, and you can split this up over and over again, as you can see, until you can get infinitely small. Well, this pattern actually doesn't go all the way infinitely small because we have these sort of unit size little cells down here, but interestingly, this one is created by just taking that pattern and repeating it again and again and again. So we can imagine, say we're starting with this little triangle pattern, and then we cut and pasted it twice to make this larger triangle pattern, and then we cut and paste that one twice to make the even larger triangle pattern, and so on until we get larger, until we keep getting larger and larger. And that's effectively what we could imagine. That's how we created this pattern, but we know that's not how we actually created this pattern. We created this pattern not by looking at the last 16 rows or 8 rows or 4 rows and so on, but by just looking at the last row only. And by only looking at the last row and computing rule 22, whatever that is, we got this interesting Serpensky triangle. Again, a Serpensky triangle is cool, and it shows up in different kind of experiments in complex systems because it has this fractal structure. So first of all, what is a fractal structure? Well, a fractal structure is a structure that repeats itself at different scales of focus. So maybe we could zoom in on this, zoom really far in as far as we like, and it would look exactly the same. Zoom far out as far as we like, and it would look exactly the same. That's what a fractal is. And lots of cool things in complex systems research have fractal structures. All right, these fractal strange attractors are pretty cool as well. And again, that might be cool enough to write a paper about it, but probably not cool enough to write a very long 1,000-page book about it. And so that's where we got to Rule 30. Now, Rule 30 is, again, as I mentioned, a sort of famous and popular one because of a couple of its properties. One is, as you can see, the pattern here, unlike the pattern for all of the other ones, is chaotic. Now, how are we defining chaotic here? That's a little bit hard to say, but the piece of it that I want to tease out is that it is unpredictable. So for instance, there's a couple different prediction games we can do here. The one that I mentioned already a couple times, what happens on row 10,000, okay? So what's happening on row 10,000? First of all, what is row 10,000? That's something we could ask. What is row 10,000 going to look like? We probably know, all of them form this kind of cool triangle structure, at least a lot of them do. So we can see it's forming this. So we probably know that on row 10,000, it's going to be a certain width. But other than that, we're not going to know which bits are flipped in the middle, okay? Or another question we could ask is, we could focus only on the center column, and of course it's going to be hard because it's very narrow, but on that center column there's actually a pattern. Now on the Serpensky triangle, that pattern is one that we could predict. So I could immediately from the Serpensky triangle just say on row 10,000, is that middle element going to be alive or dead? And I should be able to analytically, meaning without having to simulate it, know exactly what that's going to be. But with Rule 30, that is not the case. All of the ones that we've looked at so far, I can predict what row 10,000 looks like, but with Rule 30, I cannot predict what row 10,000 looks like. Now, the other side of that coin is this is a deterministic process. So I could tell you what row 10,000 is by cheating, meaning I could run it to row 10,000, remember what it is, and then come back to this video and pretend like I didn't do that. But that's the only way to know what row 10,000 is going to be, at least as far as we know, and that we have reason to believe that there are no analytical ways to find it. Now, the other real cool thing about Rule 30 is that Rule 30 has been proven to be what is called Turing complete. And on a very hand-wavy, rough way of what does that mean? That means that this rule is equal in power to a modern computer, meaning, so let's try and break that down, because what does that even mean? That's kind of a strong statement, but it's hard to cash out. Well, what that really means is if we are already very impressed at what a modern computer can do, but we know that in its brain, in the center, in its central processing unit, that really all it's doing is flipping bits. It's turning zeros into ones or ones into zeros. Maybe it's adding a couple together, whatever it's doing. At the very core, that's all it's doing. And in the same sense that what this cellular automata is doing, or any of these cellular automatas are doing, frankly, are just flipping bits. We can think each one of these cells as being a bit, and being alive or on as just being a 0 or a 1. That's actually how I simulated it in the background here, of course, right? And so that, if we think about it that way, if we think that this cellular automata, like our central processing units inside of our machines, are just really just flipping bits, then we can imagine that there's some rule about in our computer how they flip bits, and there's some rule here. We have 256 rules that we were investigating here, and some of those rules might be as powerful or following the same rules that our computer is. There's no reason to suspect that would be true. And certainly after looking at rules 0, 1, 2, and 3, and 4, and so on, which we found which were pretty boring, uninteresting, and very predictable rules, it is a little bit surprising to get to rule 30 and see this weird chaotic behavior. And sure enough, that's what Stephen Wolfram was all about as well. He was saying, you know, this is an interesting rule because it has this unpredictable behavior. And so he studied it a little bit more. And this Turing complete nature, he teased it out and then he proved it, that it was Turing complete by, now let's randomize this a little bit. Now when I randomize it, now remember my left-hand side is a wall, and that's why we're getting this sort of artifact pattern here. If it was random all the way in the all infinite, we would get a different pattern here. So maybe focus on the right half here. But when I set it up randomly here, that initial state that we set it to, we could imagine that initial state is an encoding of an input, say, to a problem that a computer wants to solve, like 5 plus 9. And we encode 5 plus 9 up there in those bits up there, maybe by just writing 5 and 9 in binary. That's a simple way to do it. The only other thing we need to do is we actually need to give it a program to run. So tell it what we want it to do is plus them together. And if we did that, if we ran it, and we ran it on rule 30, what Stephen Wolfram's proof tells us, if we wrote the 7 and the 9, or the 5 and the 9 in there, and the plus in there properly, rule 30 would add them together for us and give us the proper output. And again, what does that mean, proper output? Well, it would be just a big long line of alive and dead characters, and we would have to interpret that as saying, you know, the appropriate output. But that's the exact same thing we're doing with the machine. The machine just has a bunch of weird states of electric circuits that we choose to interpret as zeros and ones, and then we choose to interpret those as, you know, pictures of cats on the internet. So even though it's very highly abstract, and just looking at this cellular automata, it's kind of hard to say, what do you mean this is as powerful as a modern computer? On a very high abstract theoretical level, we're able to prove that, you know, we could imagine a hypothetical different universe where instead of Alan Turing coming around inventing the Turing machine, or Alonzo Church coming around and inventing the lambda calculus, we had Stephen Wolfram who came around and he invented elementary cellular automata, and with that we built computers out of this idea instead. It would have been possible, there is another universe where we've built computers out of this cellular automata idea instead of the von Neumann computer, for instance, that we have today. So the final takeaway that I want you to think about as you're reflecting on Stephen Wolfram's elementary cellular automata is that each one of these cellular automata, there's only 256 of them, each one is determined by very, very simple rules, and rules that respect this sort of principle of locality that I mentioned earlier, where the next state can only be determined by its neighbor states. Even within that very restricted space of cellular automata that we looked at, we found this rule, rule 30, that had this very powerful ability to be, we sometimes call these rules constructive because they create things. They don't really compute things. That's why it's kind of hard to think, what do you mean a computer? It creates things. It creates the next state. So we sometimes say that this is universally constructive, but to find a universally constructive rule in these 256 very, very simple rules, and of course rule 30 is not the only one that has this property in that set, was kind of amazing and interesting to find. And it had promised that there are probably out in the more wider universe of cellular automata even more interesting rules out there that can do this same powerful thing, but other cool things as well. And so that's going to lead me into our next video. In this video, we focused on this one-dimensional cellular automata. Well, of course, maybe the next thing you might be thinking of, well, what happens if we arrange these cells in 2 dimensions, or maybe even beyond that in 3 dimensions? And there's a very famous 2-dimensional cellular automata called the game of life, and that's what I'll take a look at in my next video. So thanks a lot for watching, and I'll see you in that next video.